Yes, it's working now. Thank you.
Okay, great. Thank you, first of all, to the organizers for the invitation, and thank you all for attending this talk with a rather long and perhaps confusing title. I want to start with a story that is seemingly irrelevant and also includes gross generalizations. The story has to do with with whaling, which is the practice of hunting whales for meat and fat that has started quite some time ago in the 9th century, but really picked up in the 18th century with the beginning of the Industrial Revolution because of the need for energy, and whale fat was part of that. And hunting whales was done in such a systematic and industrious way that it led to the near extinction of some whale species in the 20th century. So then in the 21st century, whaling was banned and is still banned, I think, in most countries. So that sounds like a nice story where humans saw what their actions did to another species and made decisions to stop doing these actions and protect the other species. However, we're missing an important part in this story, and that's in the 19th century. We got we started drilling for oil, and that appeared as an alternative product for energy production that was better than fat from whales. It was easy. It was easier to handle, easier to find, more available. More of it was available, and less risk of getting it. So basically, since there was an alternative, a better alternative, that resulted in the ease in which we as humans decided to ban whaling and protect another species. Otherwise, one could argue that we would have continued until we killed the last whale. So there's an important lesson to learn here. And the reason why I started with this story is that for a product to be replaced in the market, an alternative product must be available. And not only should it be available, but it must be at least equal to the existing one in terms of quality, efficiency, cost, or whatever criteria we use to decide. And these changes, this replacement might have strong socioeconomic changes and also environmental impacts. And oftentimes we prioritize socioeconomic factors to environmental. Now, going back to the oil production, we don't use crude oil as it is. We have to treat it, and the most important treatment process is the distillation, which produces fractions of oil that are used in many different applications. Most of it, as you see here, is for energy. But there is a fraction that at the beginning we didn't know what to do with that until we scientists realized or came up with plastics. Now, plastics, because of that, because the raw material for plastics is a byproduct or a waste from the process of treating crude oil for energy, that means it was very cheap. So the infrastructure investment was already in place for the energy part, and the raw material for plastics was basically free. In addition to that, that gave rise to a variety of chemicals and polymers. And in addition to that, plastics are lightweight and durable materials. So they played quite an important role in advancing our quality of life especially in the sectors of transportation. Because of the less weight and durability, transportation became cheaper, and they also contributed in improved safety for foods and health protection. However, as you know, in 2022 alone, 400 million metric tons were produced, and all this material, it's goes into products, and then it ends up in the environment. And we can already see plastics everywhere. And it's not only what we can see with our naked eye. As you all probably know, plastics will gradually break down to smaller particles, micro and nanoplastics, and we're finding those in everywhere, in the North and South Poles, in the most remote mountains, lakes, rivers, in the soils, also within humans and animals, in plankton, literally everywhere. So we have very high exposure to plastics, from large plastics to nanoplastics, and that is a cause of concern. And not only we have very high exposure, but we're also gradually finding out about the the hazard factor of plastics. And in some cases, it's mostly the additives that that induce this hazardous effect. In other ways, it can be organisms perceiving plastics as food, filling their stomach, but not really getting any nutritious stuff. So we have both very high exposure and potential for hazard. And the question is, can this stop? And one would think that one way to stop this the plastics pollution issue is to reduce at the front end the plastic products in the market by finding alternatives, as we talked as I talked about at the beginning. Another option is on the back end is phasing out from oil production. Globally, we're transitioning towards decarbonization of our energy sources. But let's take the first example. So I have two examples here. On the left, you see a cloth bag. This product is lightweight. It can be compressed, so it's quite easy to carry. It's not a big hassle to have it around and use it when needed. So actually, this product is available, and it's at least equally good as the existing option, as the existing product that is supposed to replace, which is single-use plastic bags. On the other hand, we have paper straws, which, in my opinion, have been quite a disaster. On the one hand, they don't work as well as plastic straws, because after some time in liquid, they would soak and stop functioning. And on the other hand, in order to, if you put paper in a liquid, it will soak and then slowly dissolve. In order to avoid that, you have to add plastic to the paper straw, so it defeats the purpose in the first place. So finding alternative products is not an easy task. There is some options available, but currently, of course, it's very few compared to the vast number of plastic products in the market. Now, the other option is phasing out from oil production, because one would think that since we're transitioning to decarbonization, that will lead to less oil being extracted from beneath the earth. And that would mean less raw materials for plastics. So then that will result in less plastics. But then we see something like this, which is the OPEC plus crude oil production forecast for the next couple of years. And that was before the election of President Trump. So instead of forecasting a decrease in oil production, they were forecasting a slight increase. So why is that? Since we're transitioning towards decarbonization. And the answer is that oil companies are expecting to make up losses from decreasing sales of oil, and they plan to make up with selling more chemicals and plastics. As a matter of fact, the OECD is projecting that use of plastics will almost triple by 2060. And here you can see the sectors where these plastics are expected to end up. So you have about a third being used in packaging. As we said, plastic material is very advantageous for transportation and vehicles and construction and so on. So what can we do to impact this trend that seems to be going in the direction towards more plastics ending up in the environment? As you know, we as individuals or institutions can decide to reduce the use of plastics, such as single-use products, reuse. So if you have a plastic bag that is durable that you can use for many years, that's also a positive step. Recycle, keeping though in mind that it really depends on the polymer type. For example, high-density polyethylene can be recycled up to 10 times, while polyvinyl chloride or polystyrene cannot be recycled. Remove, for example, with beach cleanup actions or picking up trash. And of course, monitor. And monitoring is very important because it gives a clear picture of the situation. And having a clear picture is paramount in order to make decisions. And that's what I will talk about in the next slides. Monitoring as a professional or as an amateur, starting with professional monitoring. So I will go through the technical stuff rather quickly. If you want, keep the references and to learn more in depth of what I will skim through. So here you see tools we use to sample for plastics on the sea surface or within the seawater body or on the sediments. Then you have to pay attention. You have to take care of organic matter because you have to simplify your sample in order to be able to isolate the plastic particles from all the organic stuff or non-plastic material. But doing that, one has to pay attention not to degrade the target material. And that's more relevant for the smaller sizes, so micro and nanoplastics for sure, and it's less relevant for larger plastics. Then you have the task of identifying plastics, and your goal is basically identifying a particle within a larger population of particles that are not plastic. And you have to start with a good definition. What is a plastic particle? And the best one I have in mind, the most structured approach is this published by Hartman and others, where they use 7 criteria that have to do with chemical composition, solid state, solubility, size, shape, structure, color, and origin. And some of these criteria are not as straightforward as one would think. For example, size. The authors here argue that nanoplastics should be considered as the plastics that have at least one dimension between 1 and 1,000 nanometers, microplastics between 1 and 1,000 micrometers. However, the majority, I would say, of scientists extend this range of microplastics to 5,000 micrometers. And that has to do with the tools that we use on the field, but mostly it has to do with regulation on solid wastes. So there is a threshold there on existing regulation for other wastes that is at 5 millimeter, and that has trickled down to plastic research. So plastics that are between 1 to 10 millimeters are proposed here as mesoplastics, and anything larger than 1 centimeter would be a macroplastic. And then you have to decide what parameter to measure in order to characterize the particles in your sample. And it's not just size and shape, as we already talked about. There's the number concentration, the agglomeration state, surface properties, composition that can be measured. Typically, you would pick number concentration or mass concentration, size, and composition as the main parameters for characterizing a sample. This example I use, I have used quite often because it gives the number concentration of particles over a very wide size range. So it starts from 10 nanometers or a few tens of nanometers to 1,000, and it goes up to 1,000 micrometers. And it shows that the researchers here had to use 3 different techniques because each technique has different ranges of applicability. And I will go through some techniques that we use often in microplastic research. We'll skim through this. Again, please keep the references if you want to learn more. So FTIR gives a chemical foot fingerprint with a limit of detection starting from 10 microns. So it's applicable to macro, meso, and part of the microplastic range. Raman spectroscopy also gives a chemical fingerprint, but with a substantially lower limit of detection starting from 1 micron. So it's applicable to macro, meso, and all microplastics. Pyrolysis GCMS gives mass concentration and polymer identification. So it's a bulk method. And the limit of detection refers to the minimum amount of the polymer in the sample in order to be detected. And that's 10 micrograms. And it's applicable to the whole size range because it doesn't, it's not a single particle method. It measures total amount of a polymer in a sample. Single particle ICP-MS can be used to produce particle number concentration and an estimation of particle size with low limit of detection starting at 10 nanometers. So it's applicable for micro and nanoplastics, not for larger particles. Scanning electron microscopy, you can measure size, shape, number, and when coupled with EDS, you can measure composition and individual particles. And the limit of detection starts at 100 nanometers, so it's applicable for micro and nanoplastics. Field flow fractionation is a pretreatment method that basically orders particles based on size and/or density. And the limit of detection starts at 1 nanometer, and it's applicable for micro and nanoplastics. And lastly, nanoparticle tracking analysis basically tracks particles in liquid by recording their movement. So you can measure the size and number concentration with a limit of detection starting at 10 nanometers. So it's applicable for micro and nanoplastics. So we produced this map with colleagues. Every method here is a different color. And the intensity of the color is showing the more dense the color, the more direct observation you can make for one of the 4 parameters shown here, which is the most common parameters: size, number, mass, and chemical composition. So for example, if you want to measure the chemical composition of the plastics in your sample, you can use FTIR, Raman, pyrolysis GCMS. You can get an estimation with single particle SPMS, SEM, EDX, and you You can also use field flow fractionation for an estimation, but you cannot use light scattering. So if you are interested about the number concentration, you can get an idea with micro FTIR, micro Raman. You cannot use pyrolysis GCMS because it's a bulk method, but you can measure, you can use single particle ICP-MS, FFF, and SENDX, not FFF. And you can also use nanoparticle tracking analysis. So me and three colleagues that Ariadne mentioned issue is a transdisciplinary issue, and it doesn't make sense. I mean, if scientists stick to their discipline and try to address it, they start with major disadvantages. So we propose that transdisciplinary collaboration is absolutely necessary. And that doesn't mean simply interdisciplinary collaboration, which means people from different disciplines collaborating, but actually training and developing ideas and concepts within disciplines from early on. And this is why we decided to initiate the plastics workshop for early career researchers to provide training in different disciplines and at an early stage, and also promote alternatives to academic careers. So also introduce the idea of working for government agencies, public outreach, industry, and nonprofits. This is a picture from our last workshop in Idstein in Germany. You can see we have Pascal here from BASF, the largest chemical company in the world, I guess. Representatives from NGOs like the Ocean Cleanup, and the rest is academics. And then another way of so that's the purpose of that, is to provide training and options to researchers at the very early stages of their career. But we're also doing work in developing citizen science projects. That's for monitoring, not professionally, but as a citizen science. So non-skilled people. There, the advantage is that you get data and samples without without having to organize sampling campaigns that is money and time consuming. So we're targeting two groups of citizen science in general. One is sailors. And the advantage there is that sailors are already technically savvy people, because sailing is a very complex sport. Arguably, it's the most difficult sport in terms of the number of parameters that you have to keep in mind. So these are people that are already familiar with technology and flexible. So it's easier for them to pick up tools and concepts that we use for measuring parameters and for taking samples. And the other idea is schools for science. Here you see Professor Argiraki explaining the idea to schools in Milos, in Methana, and in Athens. Because schools, it's easy for a school project to take samples or measurements where the school is located. When for scientists to go there on a frequent basis, as I said, would be very time and costly, time consuming and costly. So here are some examples for citizen science that you could consider if you're inclined to. If you want to monitor on the seawater surface large plastics, you can use the Ocean Cleanup Survey app. For macroplastics on the beach, there's the Remedies app and the Andromeda app for meso and macroplastics on beach. And also you can contribute to scientific projects such as the Nexus Monarch project that Professor Argiraki is coordinating. So to summarize, I would say that plastics will remain in our lives in the foreseeable future. And in order to address the plastics pollution, the inevitable plastics pollution issue, is first of all by striving for scientific excellence. And so it's not adequate anymore to just go somewhere where you can sample anyways and get a sample to see what sort of plastics are in there. You have to spend time and think about the definitions and the methods, and most of all, contamination control. And I would also say that citizen science might very well be the key to addressing the plastics pollution because of the potential to inform people through practical ways, not simply by reading or listening to something, but actually participating in in a research effort. And with that, I would like to thank you and answer any questions.
Thank you very much, Andreas, for this interesting talk. I would like to invite questions from the audience. Until I see a question in the chat box, I can start by asking you this. You have been collaborating with geoscientists for some time now in the study of microplastics, and I would like to ask you, what do you see as a role for a geoscientist in this whole topic of research?
Yeah, thank you, Ariadne. Yeah, as I stressed earlier, the issue is really transdisciplinary. And actually, one of the reasons why it became such a big issue before we started paying attention was that even though the first observations of plastic pieces in the sea and on the beaches were made several decades ago, there was a gap of more than 10 years where nobody would think that this issue is relevant to their discipline. And I think that's the wrong approach. I think all disciplines are relevant for the plastics pollution issue. And for geologists specifically, I would say it's a no-brainer for me because we know that plastics mix in the soil and they change soil properties. They're relevant for agriculture and sediments. So I think, I mean, for me, it's a no-brainer that geology is part of the solution, let's say. Does that answer your question, or were you asking for
Yes,
more specific?
I think it is pretty clear. And I see another comment and question in the chat now. So it is from Alekos Dimitriadis. The comment is that, in his opinion, reducing the use of plastics is not what the world needs. And his question is, what about banning completely the use of plastics? He strongly believes that this is the only way to somehow clean up our home planet. So what would you think? Totally banning the plastics will save the planet from the plastics?
Yeah, I think that's a noble approach, but it's not practical. So I mean, what does it mean ban plastics? Like, would you ban plastic gloves in surgeries? I mean, there's many applications that they're absolutely necessary, and there are no alternatives. Also for transport. So I think this approach that was suggested is strictly scientific, but decision making is always not based on scientific data. Often it's based on socioeconomic factors. As I said before, the example I gave with whaling was I really think that if there was no alternative, we would have killed all the whales because of the socioeconomical factors. I think typically they have more weight in decision making.
Thank you, Andreas. There is another question by Carlos. So how do you see the future of plastic pollution considering the present new issues? Even if we reduce or ban completely the use of plastics, they will persist for a long time in the environment.
Yeah, and there is efforts for removing plastics for the environment, but I mean, of course, complete removal is not possible. But for example, what ocean cleanup is doing, actually, ocean cleanup started as an effort to remove the Great Ocean Pacific patch. There's basically accumulation of plastic pieces in the Pacific Ocean, and that was the means. I mean, I was not convinced that the means made sense because of the very tiny impact that these removals have. But now they have moved to more practical solutions like removing at the source, so at the outlet of rivers, and that's a major source of plastics in the seas and oceans, and intersecting that is a big deal. I think there's no magic solutions, just initiatives and efforts that we have to keep trying. But I don't think plastics will disappear. I think the socioeconomic factors are way too strong.
Yeah, I agree. Okay, thank you very much.